Thank you, Yuta. So, hi everyone. My name is Kaan. I work as a senior research scientist at NVIDIA. And today I'll be presenting our work on manufacturing application-driven foveated near-eye displays. This work was a collaboration in between UNC, University of North Carolina at Chapel Hill, and NVIDIA. So, we would like to show a new method for manufacturing optical components using commodity 3D printers, which enabled us to build a fully untethered novel near-eye displays for augmented reality applications based on free-form optics. In the opening of this video, you have seen an optically clear 3D printed cube that we manufactured using our technique, and a diffusive 3D printed cube as it comes out of a 3D printer. The device you see that comes out of the back is a binocular untethered near-eye display with a field of view of 55 degrees by 35 degrees monocular. Supports resolution up to 11 cycles per degree. Using our manufacturing technique, we show that foveation can be part of a near-eye display without using a second display mechanism. So let me get into the details. Near-eye displays promises to be the next mobile platform, providing a gateway to countless augmented reality applications. And that will improve our day-to-day lives in the near future. However, a large body of problems regarding the near-eye displays exist today. So, field of view, dynamic range, color, resolution, form factor, power, vergence accommodation conflict, lead times, cost, and customization are all barriers to future near-eye displays. So, as scientists have lots of troubles resolving these problems, we have created a detailed survey on this that will be coming up at Eurographics, next Eurographics. So it's at the bottom of this page, and this is uploading it. I want to make sure this is visible. Okay. I hope, anyways. So this will be presented in Eurographics 2019. We'll be covering all these problems that I highlighted in a greater detail. So let's look into our proposal and try to understand the bits and pieces regarding to our proposal. We took a step to the heart of these problems in a unified fashion. Here you see the problem that I've listed before, as in the previous slide. We introduced a new near-eye display manufacturing pipeline through a multi-body proposal containing rapid prototyping technique, a new design pipeline for near-eye displays using machine learning, better insights for solving the big problem of vergence accommodation conflict, and introducing a foveation technique through optical hardware are parts of our proposal. Starting with the rapid prototyping, near-eye display hardware research, development, and production is only accessible to the chosen ones with the right resources. Changing that will accelerate the way solutions are developed today and tomorrow. So in a second, you'll be seeing a video showing our 3D printing technique. We first 3D print the material, and then we covered with the optical adhesive. Here you see some 3D printed parts from a conventional Formlabs 2D printer, covered using optical adhesive during the process. We use a vacuum former to form a smooth surface around optical adhesive covered parts. And you see me going through this process, and one target surface is covered with optical adhesive. As this is covered with the optical adhesive, the second step is to cure the optical adhesive so that you can complete the process. And to do that, we will be using a ultraviolet light source. At this stage, I'm just cutting parts around the mold so that I can get rid of it and it can be in a smaller fashion. As I do that, I just use a conventional ultraviolet light source to cure the optical adhesive. The interesting insight here is when you cover 3D printed parts with optical adhesives, and if you use a PET plastic, the PET plastic does not bond to the optical adhesive, but it bonds to the 3D printed part. So at the end of this entire process, you can basically get rid of the vacuum formed part and use only the 3D printed part covered with optical adhesive. I will quickly jump to a little, oh yeah, this is. So you see me removing all these plastics around the optical adhesive, and I'm just getting rid of this PET plastic. So, but why is this important at all? So infrastructure for prototyping fast pace in today's world is a gigantic investment. As you can see, if you want to do all these steps in-house, I mean, in the traditional means, you need a large investment up to maybe $5 million, and you need a permanent technical employees to do that. So prototyping is not accessible to all researchers. We are hoping to change that. So we use a Formlabs 2D printer, which is below $5,000, a Formec 508 DT vacuum former, an off-the-shelf Norland 68 optical adhesive, which can be found in many optical laboratories, and just a clear PET plastic. So we combine all of these things, and the investment cost here is around maximum $20,000. And with enough training and few try and error, you can also do it yourself. You don't need external people to help you with this stage. So note that at the given stage, as in the way I'm introducing all these, it's good for prototyping, but not for the final product. Of course, for serious 3D, serious optical parts, you need metrology to be in the place. So this is good for covering the steps in between for prototyping before you land on the final problem, final solution. Here are some results coming out of our manufacturing technique: lenses, waveguides, which has total internal reflections inside, and diffusers can all be 3D printed. Here you see a photograph as a comparison. Photograph A shows an actual optical glass-based off-the-shelf lens. To be accurate, it's LA1401 from Thorlabs, and photograph B is showing our replica of the 3D printed version. Yet another excitement for this opportunity is a 3D printed prescription glasses. This is one prototype we built in-house using our technique. So next, I'm going to introduce you our machine learning approach for designing key optical components of our near-eye display. The two most common optical layouts in augmented reality near-eye display architectures are bird-bath optics and off-axis optics. In bird-bath optics, typically a flat screen is reflected off a beam splitter and a beam combiner to relay an image from a flat screen to an observer's eye. A product example of a bird-bath optics is Disney Lenovo's near-eye display that you can buy today. A product example of a off-axis. Before jumping to that, let me explain the off-axis. The off-axis optics eliminate beam splitter and directly redirects a tilted flat screen using only a beam combiner. Meta 2 is a product example of for an off-axis geometry. So we revisit both bird-bath and off-axis optical design using our manufacturing technique and a design methodology that uses machine learning and ray tracing. We built projection surfaces that leads to free-form curved screens that can deliver optical qualities depending on the requested experience. In the most simplistic terms, details are present in our paper, we ray trace from a target depth curvature to identify point candidates to form a free-form projection surface using a least square optimizer. we use each depth point corresponding to a freeform projection surface point as the training data. And at the next step, we use a Gaussian process regression model and the training data. So we build a regression model out of this optimization. And finally, for a given input depth map, all we estimate is the new surfaces using the regression models at a rapid fashion with respect to solving each point one by one with an optimizer. Note that our model can either find a solution using a fixed eye location, which we name as conventional mode, or it can provide custom solution for a given eye location and eye rotation as well, which we like to name as gaze adaptive mode. So here in this example, you see a free-form diffuser in a second, hopefully, that we produce using our manufacturing technique and our machine learning algorithm. This particular one has true freeform, as the content that is wanted to be shown is a man with a wine glass at his hand. Note that one side of the printed component is diffusive and the other side is optically clear. Rest of the video shows how does such a diffuser look like through our handheld static prototype based on bird bath optics. You get this occlusion effect as the camera moves inside the eye box of our prototype. This is a proof to show that our diffusers can be in arbitrary shapes targeting any particular application desired. So to understand the needs of future augmented reality application, we looked into natural scenes and we tried to understand their depth information so that we can target the right shape for our optical diffusers. We looked into 4 different possible natural scenarios to understand their needs when it comes to the augmentation. So these are walking indoors, social interaction, working at desk, and office workspace. We found some of these data sets and we record some of these data sets for further evaluation. Some of these recordings additionally contain gaze information. For the ones that has no gaze data, we relied on the state-of-the-art saliency predictors that we can find in the literature. Using the data sets and gaze locations as the weighting, we analyzed the depth requirement for each use case. So we observed that depth requirements for walking indoors and social interaction and office workspace are less diverse in depth. So it more or less stays within the depth of field of an average human eye observer for most of the time. And probably a single free-form surface designed for them may serve well in applications involving these depth conditions. However, working at desk scenarios suggest that there should be more than one surface, possibly 3 surfaces might be feasible for that given depth levels. Of course, 3 surfaces per eye. And here is a slightly more sophisticated example. In this case, we made a progressive diffusive surface for our bird bath-based prototype with projectors. Here you see 2 targets in our scene, a dinosaur and a puppet standing at different distances. I want you to pay attention to the focus of the camera. I will switch from dinosaur to the puppet at one point, and bottom and top portion of the USAF chart will be in focus accordingly. Now I'm doing the focus switch. The top is more blurry, and the bottom is more sharp in this case. So we redesigned the projection optics of our projectors using our 3D printed optics. And we tried to provide a built-in foveation in hardware, covering the entire field of view of a projection screen used in our prototype. Here you see a sketch showing a foveated lens for a projector. Please pay attention to the checkerboard pattern and how pixels are becoming denser at the central region. And here you see what's coming out of our test bench with such a projection lens that we manufacture using 3D printers. From A to C, we show that the high resolution part of a foveated projection lens shift from left to right by moving the projection lens in front of a projector. So to accommodate such a motion in an optical system, we basically use, as a proof of concept, a spring-loaded mechanism in our static prototype. Here you see the same static prototype that I showed before, but this time it has a spring load, a mechanical spring load that you'll be seeing. Let's see. This is the spring. So basically a small, tiny motion in front of a projector will get your content to be projected at a different visual field of view, and you can do this in a foveated fashion. Here are the conclusion marks. Back to our proposal slide. We imagine new near-eye displays with free forms, and we also imagine that all these solutions can be prototyped in a rapid fashion using 3D printed optics. So we provided a rapid prototyping technique in this case. And our machine learning algorithm helped us design these freeform optics to fight vergence accommodation conflict for a selected application. We looked into natural scenes to give an idea on depth requirements of various use cases. Finally, the foveation in hardware with a single projector made possible through a custom designed projection lens with a mechanical mechanism. We show that such a lens, by moving it mechanically, we can steer the content in the to different portions of the field of view. So in the past, we gave a demo of our complete near-eye display prototype at SIGGRAPH 2018 Emerging Technologies show floor. Gave a chance to many visitors to experience the outcome. And here you see some photographs showing people looking through our prototypes. At that time, we weren't able to talk about the technical details of our prototypes at a greater level. Now that our work is public and you can also download and read our paper, anybody can learn more about the technical details. Anybody can replicate this work from now on. And I'm also proud to say that our demos helped us returning back to home with an award, Best in Show award at SIGGRAPH 2018. With this limited time, I try to introduce our work. I thank to my collaborators from UNC. I want to highlight that I'm always happy to talk to bright and wise future collaborators at every level. And I would like to finally also highlight one more thing. One of my collaborators, Kylie, has an awesome posters at the poster session. If you have time, please look at her poster as well. Her work deserves your attention. I'll be more than happy to take your questions, and thank you very much.